All right, so here's a problem. Find the critical numbers for these three functions. Again, remember that a critical number is where the derivative, so if you have a function f of x, a critical number is where f prime of c is either 0 or undefined. All right? So often when I start these problems, I think to myself about the domain, and then I go through this. So we'll start with f of x. I look at it, it's polynomial. Everybody agree? Has a domain of all reals. I'm not even going to bother writing it. So the first thing I'm going to do then is take the derivative, because I know I have to get the derivative equal to 0 this time. When I take the derivative, does everybody agree the derivative is also a polynomial in blue? Domain of all reals on that. So I don't have to worry about, I'll tell you right now, f prime is never undefined. Does everybody agree with that idea? It's defined everywhere. But I have to know the zeros. So if I move this stuff down a little bit, I'm going to say, okay, let's make 0 equal this. I'm going to guess, I took it from the book, I'm going to always try to factor first. All right? And looky, looky, looky. How about plus 1 minus 1? That works. So there are two critical points to this function, or two critical numbers. I know f prime of c equals 0 when c equals -1 and positive 1/3. Every one. I am not doing anything about whether they're max or mins yet, or global max or mins. I'm just saying these are points where that may or may not happen. These are critical points that occur at -1 and 1/3. All right. That was a simple power rule for derivative. You guys agree? Pretty easy derivative. All right, so we'll box all that. We'll just move that out of our way. The next one up was let's find the critical numbers of g of x. Everybody, two ways to handle g of x. I'm going to do it as a quotient rule because I think it's good practice. We could do this as a product rule if we rewrote it this way. Does everybody agree? You could do this as a product rule with a chain if you did it this way. But it doesn't gain you much, okay? So we will do it as a quotient rule, all right? And I'll just erase that. So the first thing, again, I want to think of is what's the domain of g of x? Well, it's a rational function, so it's all reals except where the bottom is 0. So, yeah, I'd have to do some work here to figure out the zeros, right? So I'd have to say, well, I'm going to set x squared plus x plus 1 equal to 0. Now you could do quadratic formula, which we don't do often, or like Mr. Anderson seems to always do, right? I can complete the square pretty fast here. And I'm going to stop right here, because when I start completing the square, you guys will notice it's going to be -3/4. So when I solve this, take the square root, I'm going to get an imaginary number. You guys see it? The square root of -3/4 is I. So guess what? There are no zeros on this one. So again, the domain of this function, and I know this is a lot of pre-calc I did awfully fast. I know the bottom can never be 0. I just proved that it doesn't intersect that, okay? It's a parabola, you could graph it, but I know the domain's all reals. So now where am I? Well, okay, I know the domain's all reals of this rational function. I got to get a derivative. G prime of x. Derivative of the top. Derivative of x plus 1 is just 1. Times the bottom. Minus the top times the derivative of the bottom, which is derivative of x squared plus x plus 1 is 2x plus 1. All over the bottom squared. The nice part is we've proven already the bottom can never be 0, right? We know that. So g prime of x is not undefined. But we do have to take some time here and clean up the numerator, because we are going to have to set g prime of x equal to 0. All right. And I would write it as x squared plus x plus 1 minus 2x squared plus x plus 2x plus 1. I just multiplied the binomials. And then I'll just probably cheat a little bit here, and that's all over j squared. And if you've been in my class before, you know I mean junk squared. We're going to rewrite the junk here in a second. So I see x squared minus 2x squared is negative x squared. I see x, minus is in. I see x minus 3x, which is negative 2x. I see 1 minus 1, I get 0. Oh, look at that. Isn't the numerator really cool? Because when I write the denominator again, squared. So if I set this equal to 0 now, right? I set this equal to 0. The bottom is not ever going to be 0. Okay, we've proven that up originally. All right. So now I look and I know that I just got to figure out the places where the numerator of the derivative is 0. This is a factoring problem. All right, this is a factoring problem. So I would say negative x minus 2x equals 0. And I pull out the negative x and I get x plus 2 equals 0. And everybody, at this point, we all see the solutions to this great equation at the bottom are 0 and negative 2. So I know that f prime of c equals 0 at c equals 0 and negative 2. My critical numbers for this function are 0 and negative 2. And everybody, I did this awfully fast, but it's always the same. It's just a ton of practice and a ton of algebra. We're pretty good at taking derivatives, but now a lot of this falls into just pre-calculus form. All right? And again, I should make a clear point here before I go on to the next problem. 0 and negative 2 are in the domain. Does everybody agree? It is very possible to get answers here that sometimes aren't in the domain. So the numbers have to be in the domain to be critical numbers or critical points. All right. Let's move all that to the left. So let's move up the last function today. H of x. All right. Again, h of x equals x to the third minus x to the negative 2/3. So in my head, I think of this, personally, I think of the cube root of x minus 1 over the cube root of x squared. And immediately I recognize one thing. The domain of this is not all reals. Does everybody agree? The domain of this function is all reals except x can't be 0. So I would write this all right. That is the domain of the original function. I am going to move this aside. I really don't need it. I don't want it. That just helped me get started. I'm going to take the derivative of that using the power rule, and I'm going to write h prime of x is equal to 1/3 x to the negative 2/3. Negative 2/3 times the negative is plus 2/3 x to the negative 5/3. All right. I recognize 0 makes the derivative undefined, but 0 is not in the domain. So it won't be a critical number, guys. But we're going to have to get this to a single term. So this is a math exercise. I know I got to set h prime to 0, but I better start with this mess. And if I'm going to solve this to 0 eventually, I need this to be one term. So I got to get a common denominator. You guys see it? 3x to the 2/3 and 3x to the 5/3. I think the common denominator is 3x to the 5/3. Because if I multiply by x on this one, x to the 2/3 and x to the 3/3, right? 3 over 3 becomes the common denominator of, and this kills us. A lot of times I do this and you say, oh yeah, I see this now, but you don't see it until it gets shown. So this is where the practice comes in, because this is not calculus right here, guys. This is not calculus. This is just us solving an ugly rational expression, right? So everybody, I look at this and I say, hey, where is h prime of equal to 0 or undefined? And you might think to yourself, it's undefined when c is 0, and you're right, because that would make the bottom 0. It does make the bottom 0, right? And you can put 0 in for x. But the problem is 0 is not in the domain. So I would just ignore that, right? What makes this 0? I don't even want to solve it. What makes the numerator 0? We should all see it. -2. So H prime of C is when C is equal to -2. I do the double check. Is -2 in my domain? Yes, it is. And I have found the critical point of this little ugly composite function, right, of Royce. All right, everyone, a lot of this is pre-calc. It's a lot of algebra 2. It needs to be practiced, that's all right? Keep practicing.